Welcome back to Learning as a Hobby, everybody. I'm going to be going over the exercises for the recommended exercises for Multivariable Mathematics by Theodore Shifrin. We're going to do the recommended exercises for section 1.2. So let me jump right into that. There are not that many problems that he recommends in this section, even though there are many problems in the exercise set for section 1.2. I think there's like 25 problems or something. Most of them have like a geometric flavor to them, but I'm only going to do the ones that he recommends here. So I think there's like 4 of them or something. So we'll go through my solutions here, starting with question number 9. So in question number 9, he gives us these two, or he's defining these two vectors. And actually, I should probably have these subscripted, let's say xn, yn, because they have n components. So these are elements of Rn. And we define x to be the vector in Rn, where all the entries are 1. Yn is the vector in Rn, where all the entries look like this. So, first entry is 1, second entry is 2, and so on all the way up to the nth entry being equal to n. And then we define the angle theta n to be the angle between those two vectors in Rn. And he wants us to find the limit as n goes to infinity of theta n. And then he does give a hint here for this when he says recall the formulas for the sum of the first n integers and the sum of the first n squares of the integers. And if you recall, or if you watched the video, we actually derived the formulas for these in Spivak. So we derived these formulas in Spivak. So if you haven't watched the exercises for, when did we do this? I think it was chapter 2 that the exercises for chapter 2 where we did the formulas for that. I broke the exercises in Spivak into 2 videos. I think it's in the second part. So if you want to see where those formulas are derived and proven, you can check out that video for the exercises in Spivak chapter 2. But anyway, I'm just going to use them here. I'm not going to derive them. So here's my answer. So if you take the limit as n goes to infinity of theta n by the formula length x, length y, cosine theta equals x dot y. This was a formula that we derived in the section section 2 in chapter 1 of Shifrin. So I'm using that formula here. I solved for theta. And if you take the limit of this as n goes to infinity and you expand everything out, that's the same thing as the limit of this. So if you notice inside the arc cosine, 1 times 1 plus 1 times 2 plus 1 times 3 and so on, that gives you the sum of the first n integers in the numerator. And then the length of x is the square root of the sum of 1 with itself n times. And then the length of y will be the square root of the sum of the first n squares of integers. All right, and then using the formulas for those things, so this is equal to the sum of the first n integers. Under the radical here, this formula is equal to the sum of the first n squares of natural numbers, and then 1 added to itself n times is equal to n. So I'm just replacing those sums with those formulas. And then once you have that, you just simplify everything. Let me just erase this so it's not so cluttered. All right, when you simplify everything, you end up with this expression in here, and then I can take the limit. So if you take the limit as n goes to infinity, this goes to 0, this goes to 0. So you end up with square root of 6 inside the arc cosine. You end up with square root of 6 over 2 times 1 over square root of 2. And then when you reduce, you end up with inverse cosine of radical 3 over 2. And if you remember your trigonometry, that's equal to pi over 6. Right, so that was kind of a fun little problem to do. Not too difficult, but it was kind of neat that the angle approaches pi over 6 as um, the dimension of the space goes up to infinity. So that's kind of interesting. The next one he suggests is question number 14. Let me read it out. So I'll move this up a little bit. So he says, use vector methods to prove that a triangle inscribed in a circle and having a diameter as one of its sides must be a right triangle. And he gives this figure in the book so you can visualize it. And you'll have to pretend that that's a circle because writing with the XP pen, unfortunately, it's kind of hard to be accurate when you're drawing things. The picture that he gives in the textbook is actually the parts of the picture that are in black. I drew in myself the red vectors u and v, and the reason I drew that is just I wanted the picture to illustrate them because I defined them in my proof just so you could see it visually what I'm talking about when I define u and v. So that's what u and v are. U is this vector here, and v is this vector here. Okay. All right, so let's go to the proof. Right, so here I'm defining u and v, so let u be the vector x plus y. Y is the x and y are radii of the circle here, and then the diameter is just 2x. So you have x and x for the diameter, so 2x. All right, so u is defined to be x plus y, v is defined to be x minus y, and like I said, those are the vectors that I drew in the picture. If you look at the length of u squared plus the length of v squared, just using their definition, that's the same thing as the length of x plus y squared plus the length of x minus y squared, and then expanding using the definition of the length of a vector squared and what we know about dot products, because that's what we went over in this section. You get this expression here, and notice that these cancel out, and you have 2 of these and 2 of these. So you end up with 2 times the length of x squared plus 2 times the length of y squared. And if we go back to the picture real quick, notice that x and y have the same length because they're both radii of this circle, right? This is a radii, this is a radius, and this is a radius. So length x equals length y. X doesn't, just to be clear, x is not equal to y, but the lengths are equal. Right, so I use that fact to continue the proof. So over here, this is equal to 2 times the length of x squared because the length of x is equal to the length of y. So you end up with double of these, or in other words, 4 times the length of x squared, which is the same thing as 2x all squared. And you can write this way. And notice that's the same thing as the length of u plus v squared. And again, using the definition of the length of this thing, that's equal to this. And notice that on the left-hand side, actually, let me just move this up a little. On the left-hand side, I have this. On the right-hand side, I have this. This cancels with that. This cancels with that. And that leaves me with 2u dot v equals 0, or in other words, u dot v equals 0. And by the definition of orthogonality, that means that u and v are orthogonal, which means that the theorem is proved. In other words, this has to be a right angle, or one of the vectors. One of the vectors is 0, which I guess would happen, once you go all the way down to the diameter here. Whoops. All right. That was number, what was that, 14? Okay, now the next one was number 17. All right, here he wants us to prove that for any vectors x, y, and Rn, we have length x minus length y less than or equal to length x minus y, and then he wants us to use that to deduce that the absolute value of length x minus length y is less than or equal to the length of x minus y. And he gives a hint also. He says apply corollary 2.4 directly. Corollary 2.4 is the triangle inequality. All right, so that's what I did. So you can write the length of x as the length of x minus y plus y. That's because these give you if you add those together, you get the zero vector, and that doesn't change the value. So it's like adding zero. So those two things are equal. And then by the triangle inequality, this is less than or equal to that. And then you just subtract the length of y from both sides, and you get this inequality. Right, and then we could do a similar thing, just the other way around. We can write the length of y as the length of y minus x plus x. That's the same thing as length y minus x. Sorry, that's less than or equal to length of y minus x plus length of x. And then again, you just subtract y from both sides and subtract length y minus x from both sides, and that gives you the left-hand side of the triple inequality, and taken together, that gives you this, which is what they wanted us to derive. All right, that was 17, I think. Yeah, number 17. Number 20, is this I think this might be the last one. Oh, no, this. Oh, right, because there's two parts to number 20. So this is the last problem for this exercise set that I did. 20A says, let x and y be vectors with length x equals length y. Prove that the vector x plus y bisects the angle between x and y. Bisect meaning, it cuts it in half. So, all right, here's my proof. Let alpha be the angle between x and x plus y, and beta be the angle between y and x plus y. Then if I take the dot product of x with x plus y and the dot product of y with x plus y, when you multiply that out and simplify, you'll see that you get both of those are equal to this expression, which means that this is equal to that. And since those two things are equal, this thing is equal to this, and this is equal to this. But from the hypothesis, we know that length of y is equal to the length of x. So we get that the blue expression is equal to the last expression on the right-hand side. And notice that we can cancel these, and that gives us that cosine of alpha is equal to cosine of beta. And that implies that alpha is equal to beta because alpha and beta have to be acute, so they have to be between 0 and pi over 2. Then if we say define theta to be the angle between x and y, then that means, just by the way that we defined alpha and beta, theta has to be alpha plus beta. But since alpha and beta are equal, that means that theta is equal to 2 alpha, and it's also equal to 2 beta, which means that alpha has to equal beta, has to equal theta over 2, or in other words, the vector x plus y bisects the angle between x and y. All right, that was part A. And then part B says more generally, if x and y are arbitrary non-zero vectors, let A be the length of x and B be the length of y. And they ask us to prove that the vector bx plus ay bisects the angle between x and y. Okay, so here's my proof. If you look at the length of bx, that's equal to length x times length y by the definition of B. And that's actually the same thing as the length of ay, again, by the way we defined the scalar a. So both of those things have the same length. which means that ax plus by bisects the angle between bx and ay. That follows from what we did in part A. Also, bx is parallel to the vector x because it's a scalar multiple of it. And same thing for ay, it's parallel to y because it's a scalar multiple of it. Therefore, the angle between x and y is bisected by bx plus ay, since the angle between x and y is the same as the angle between bx and by. Okay, and that's the proof of number 20. Relatively short problems, but again, we're still kind of at the beginning of the book, so that was the exercises that I did for section 1.2. Like I said, there's a lot more exercises for that section. I think there's like around 25 problems. The majority of them are very geometric in their flavor, and some of these are that I did as well. But these were the ones. So he says in the book, if you didn't watch the first video on this book that I made for multivariable mathematics, the video that I did for it. Sorry, I'm getting tongue-tied here. He labels the problems that are referenced later on in the book with a sharp symbol, meaning, it looks something like that, like sharp symbol for music. So I basically I did the ones that have had the sharp symbol next to them. And that was the ones that I did here. So, all right. So let me just stop the screen share for a second. The next video that I'm going to do is I'm going to go back to Spivak. I'm going to go write down my notes for his chapter 3. Then we'll do the video. I'll do the video of the exercises, selected exercises from chapter 3 in Spivak. Then I'll come back to Shifrin again, and I'll do the notes for section 1.3, and we'll do the exercises for 1.3, and then I'll just go down. I'll keep rotating around. So then I'll go back to Simmons, then Taylor, then Agsler, and then come back around to Spivak. And that's what I'm going to do from now on. So I'm just going to rotate through those 5 classes like that until we get to the end of them. All right, guys, I hope you enjoyed this video. If you want to see more content like this, please like and subscribe. It helps the channel grow, and I'll see you guys in the next video. Until then, keep learning.